Hi there, let's talk about functions for a while. How about that? All right, we'll start off with something really easy. A relation is a set of ordered pairs. This might seem rather inclusive or not very definitive. However, that's the whole idea. Something really simple, just a set of ordered pairs. You can think of numbers if you like. You can make up some weird stuff. If you want some weird stuff, ask me in class. I'll set you straight with some really unusual stuff. Now, the important thing is what is a function? The reason we started off with relations is a function is a special relation, a very special relation. What this does is, let's use x's and y's for example. For any x that you pick, that function only pairs it with a singular y. So for example, like this, y equals 4x squared. No matter what number you put in where the x is, you're only going to get one result for y. If you think of it in terms of a calculator, you put a number in, do some things with it. How many answers do you get? One. So your calculator is a form of a function. So remember, a function, it's a relation, so it's ordered pairs. For each first component, you get exactly one value of the second component. And we're going to show you several different ways of looking at this. Here we go. Is it a function? Well, does each x map or pair with a unique y? 1 is paired only with a 2. I don't see any 1s over here doing something else. -2 is paired with a 4. There's no other -2s pairing with something else, so we're in good shape. And 3 is matched with 4. So this is a function. And there's one way of looking at the x values and the y values. This is the important part right here. These arrows represent what corresponds to what. If each one of these up here is matched with exactly one in the second set, you've got a function. Now don't worry about the 4s. All we care about is if you pick an x, how many things it's paired with. If it's only ever matched with one y value or one second coordinate, you've got yourself a function. How about this one? Take a look at that for a second. Hit pause if you like. Always hit pause if you really want to try to learn something. Okay, this is a relation because it's got a bunch of ordered pairs, period. That's why relation is so simple. However, 1 is matched with 1, but 1 is also matched with 2. Not good. That's not a function. Not a function. And you can match, notice up here, there are only 2 different x's. That's why we've got this set. Those are the x values of function or relation G. Those are the y values. Those are the correspondence. This is in red because that stops it from being a function. 1 is paired with more than one thing as its second coordinate. Next, how about this one? Is this a function? -4, well, that's the only thing -4 goes to. -2 goes to 1, but also -2 goes to 0. Is it a function? No. It's a relation because it's a set of ordered pairs, but not a function because of these two right here. and -2 going to 1 and 0 makes it not a function. And there in red is the explanation of why. You've got the same x value, different y values, not a function. Here's another way of looking at it. Relations are just matching up x's with y's, or first things, first objects with second objects. One way of describing that is by using arrows from one set to another set. So this arrow right here corresponds to the ordered pair 1, 2. This one corresponds to -2, 4. And this arrow corresponds to 3, 4. And you can see that's a function because all these x's are different. That's good. That's one way of telling whether it's a function if you've got ordered pairs. Are all the x's different? That means you won't have an x that goes to two different y's if you only see a singular x to begin with. This one is not a function. Now look back at this one. See how every one on the left goes to exactly one on the right. And this one, this is the problem because -2 is matched up with two different numbers. Not good. Not a function. Another way we sometimes describe them as the independent variable, if you want to think of x's and y's, it's usually x's, and dependent variable y. Because you can choose an x, and sometimes you're allowed to choose any x at all, but once you choose that x, your function or relation, function in this case, insists that you've got a unique second coordinate. Pick any x, there's only one number that's going to be matched up with. Independent, because you can choose any x, so it's independent. Y, once the x is chosen, y is automatic. Domain and range, real simple. Domain is just a set of all first coordinates, and the range is a set of all y coordinates. So what's the domain and range of this one? Well, we'll just use D for domain. All you need to do is list all the x values. We've got 3 here, so we'll put 3 in. We've got 4 here. There we go. We've got 4 there. We don't repeat the 4s because it's a set. We just want to know what's there and what's not in there. And we've also got a 6. That's our domain for that relation. Now what's the range? Use an R to represent range. The range represents all the second coordinates. So we'll just go down the list. -1, 2, 5, and 8. Notice they're all different, so we have to list all of them. Domain and range on this one. This is just like ordered pairs. This first one corresponds to 4, 100. Second one, 6, 200, and so on. Is it a function? Oh, ask yourself, if you pick any of these numbers over here, for example, a 4, how many numbers over here is it matched with? If it's only ever matched with one y value or one second coordinate, it's a function. 4 goes with 100, that's only one thing. 6 with 200, good. 7, 300, good. -3, 300, good. We've got ourselves a function. Here's another way of looking at it. We can have a table of x and y values. Is it a function? Well, one thing you can tell right off the bat is that all the x's are different. That makes it a function right away. Because the only way for it not to be a function if you have the same x going to different y's. And if all your x's are different, you've got a function on your hands. Now this looks a bit strange maybe. -5 goes to 2, 0 goes to 2, and 5 goes to 2. That's fine. Duplications in the second coordinate, as you look at the mapping, are fine. Just make sure the first coordinates are all different. Domain and range here, just another way of looking at it. So domain, how about you pause this video and see if you can figure it out. Remember, you want the first coordinates. So go to each one of those points, put in the first coordinate. When you've got that, figure out what the range is. Those will be all the different y coordinates. And then come back. All right, did you get them? Hope so. How about the domain and range of this one? This isn't quite as easy because it means that we have to work with more than just a few ordered pairs. Excuse me. So we have to be a little bit careful about this one. So first of all, what's the domain? Well, the domain represents all the x's. So if you think of scanning with your eyes from left to right, what's the first x that's actually used? A -4. What's the last x that's used? A +4. So the domain is going to be the set of all x such that x is greater than or equal to -4 and less than or equal to +4. There's your domain. What's the range? Now hopefully once I've done this, you might be able to guess what the range is. Now the domain was all the x's, talking about those. The range is all the y's, so we'll be talking about all those. And again, scan from negatives to positives, in this case, from the bottom to the top. Well, the first one we're actually using is a -6. So we've got the set of all y such that, excuse me again, -6 less than or equal to y. Notice -6 will be included here, so use that equals. And less than or equal to, how high does it go? 6, no higher. Those give you your domain and range. And these are different ways of describing those sets that I mentioned in set builder notation. How about the domain and range here? What's the domain? Well, domain, all the x's. What's the first x that you run into that's used? Remember, this is an arrow, so this continues indefinitely. Well, if that's the case, then there is no first x. So -infinity would be where the x's start. Excuse me again. Where did they stop? Well, it keeps going because this line doesn't stop. So there's no end to those either. There is your domain, all real numbers. Now that's pretty simple. Now can you do the second one? We're talking about y, so we're talking about which of these numbers we're going to use. So let's start at the bottom. Is there a bottom y value? No. Since there isn't a bottom y value, it's -infinity. Is there a top one? No, because it keeps going up. Positive infinity. Both the domain and range represents a set of real numbers. Now, sometimes, just for your information, I'll describe the set of real numbers as, and I'll use something like this, sort of a fancy R to represent all real numbers. How about this one? Can you do this by yourself? Hit the pause, write down your answer, and come on back. Okay, you're back? Well, domain. What x's are used? Everything. And the y's? The y's start down here at -3 and use all y values up there. So the domain is all real numbers. The range starts at -3 and goes up to positive infinity. Next, typically the domain is all real numbers. Typically. Any numbers you can use for the x value is one way of putting it. Vertical line test. In other words, is it a function? So what I do is if I've got a graph, I'll think on the left-hand side as having a vertical line. And what I do with that vertical line is I imagine it sliding further and further to the right. As it does that vertical line ever intersect the graph in more than one point? If it does, it's not a function. If it only ever hits it 1 or 0 times, then it's a function. Vertical line test. If you've got the graph, check out the vertical line test, see if it's a function. So here's one you can try. So start on the left here. Imagine you have a vertical line and we're going to move left. Well, the first point it runs into is right here, and there's only one point on that vertical line. Slide over on this vertical line. It only connects on one point. On this one, again, only one point, so we're good. And over here, only one point. So it's a function. I guess I could clear those so you can see that just a little bit better. There you go. Their lines look a little bit better than mine. So we do have a function. Next, is this one a function? Look at that red line. That's a vertical line. So if we started over here with a vertical line and kept moving it to the right, this is one of those places we could end up in, has two different y values. Hits it in more than one place on that vertical line. So it's not a function. Next, how about this one? Is this a function? Well, again, start with this vertical line, move it to the right. And this is just one example of a vertical line, and it crosses exactly once. If you move it over here, it still only hits it one time. So lines that are not vertical are functions. How about this one? Is that a function? Yes, it is. Scanning that vertical line from left to right, it'll only ever cross that function line, the blue one time. Here's one example right here. So it's a function. Next, see if it defines y as a function of x and gives domain and range. Well, here's a tip. If you can write this as y equals with that single y on the left-hand side by itself, It's a function, period. Because this says, okay, what am I going to do to calculate the y value? As long as you've got regular arithmetic functions, arithmetic operations, excuse me, you only get one answer. It's like putting this in the calculator. How many answers does the calculator give you? One. So it's a function. Domain and range, you can use anything for x, which means negative infinity to positive infinity. Two different ways of looking at it. Remember, I said sometimes I might use this. It's the same thing as the other two. And the range, same. That's true of all linear functions, period. Is this a function? And give the domain and range. Well, if I put a number in for x, how many y values can I get back? Well, you double your number, subtract 1, take the square root. How many answers do you get? 1. So it's a function. About the domain. Okay, we've got something interesting going here. Because notice that the 2x minus 1 can't be negative. We can't take the square root of a negative number, which means 2x minus 1 has to be greater than or equal to 0. And since we write this, we can solve that for x. Add a positive 1 to both sides. We get that. Divide by 2. And since I'm divided by a positive number, this greater than or equal to does not change. Still greater than or equal to. And these are the numbers in my domain. If we want to write that in interval notation, notice it starts at 1/2 and goes up. So start at 1/2. 1/2 is included, so we have the bracket. Where does it end? It doesn't end. There's your domain. Now, what about the range? What can we get out of this? Well, when you get square roots, in general, you have a positive square root and a negative square root, two different answers. However, this one only mentions the principal square root with a positive square root. So this number right here, after you take the square root, can't be negative. So what is the range? The range is, it could be a 0, and it could be anything bigger than that. There's your range. And there you go. How about this one? Okay. Remember that tip I gave you a few minutes ago? Can you write this like that? Well, let's see. If I'm going to go from y squared to y, I'm going to have to take the square root. So square root of y squared on one side, square root of x on the other side. Square root of y squared, y, but there are two square roots of x, which means for every x, you're going to get two answers for y, except in the case of 0. So it's not a function. Domain and range, what x's can you use? Well, the x's can't be negative because you're squaring the y. So the x's for the domain will be, could be a 0, and anything bigger than that. How about the range? What y values can you get? Well, you're only putting positive numbers in for x. You're taking the square root to get y. So 0 is a possibility, and again, infinity. Oops, I made a mistake, didn't I? So this one, remember, when you take the square root over here, you get positives and negatives for y. Is this a function? Give the domain and range. Y is a function if every value of x leads to one value of y. So try this. You have values 1, 0, 1, -1, 1, -2. They all satisfy that inequality. Notice you've got an x that corresponds to 3 different values. So it's not a function. How about this one? Does it define a function? Well, ask yourself, if you put numbers in for x, excuse me, put a number in for x, how many y's do you get back? Well, you take 5 divided by x reduced by 1, you're only going to get one answer. So you have a function. Also notice that one y was all by itself, and the other expression may have x's, may not have x's, but whatever this amounts to, you only get one answer for the y, so that makes it a function. What's the domain and range? Well, let's take a look at the domain. Now here's something you want to write down, because notice with this 5 over x minus 1, well, 5 can be divided by just about anything except 0. So this number cannot be allowed to be 0. So x minus 1 is not equal to 0. Now, even though this is not equal, we can solve this for x. Add 1 to both sides. X is not going to be equal to a positive 1. So your domain will be everything except positive 1, which means negative infinity up to 1, not including 1, and then everything on the other side of 1. Those two put together make up the domain. What's the range? Well, once you put a number in here, 5 divided by some number, you get everything. So the range is real numbers. So here are 3 variations of the definition of a function. You might read through these real carefully, compare them. I've already discussed these, and decide which ones you understand better than the other. Maybe there's one of these that you'll sort of use as your standard, but you really ought to know all 3, depending on how your relation is defined. You might want to use this, you might want to use this, or this as your definition. Now here's some notation. Just notation, that's all it is. We usually put a name with our function, and our function values are y values. These two are the same thing. So if you write y equals 3x minus 7, Or if you write f of x equals 3x minus 7, you're talking about the same thing. The difference is that, first of all, this has a name. It's function f. Second of all, that to get values of y, this is how you're going to calculate them. Next, one other thing. Notice that this does not mean you're multiplying f times x. It means your function value at a value x. For example, f of 2. First of all, you're using this function, which is this one right here. And this part right here means you're going to take the 2 and place it where the x's are in the function and get your answer. So here's your 3x minus 5 with the 2 put in where the x is. Just evaluate that, and there's your second coordinate. So this, another way of looking at it is, you got an x of 2 and a y of 1. So f of 2 equals 1 can also be described with an ordered pair. This is the x, that's the y that gets matched up with it. And this is described as f at 2, function f at an x value of 2. So here's the name of the function. Quite often we'll use f for the function name, or g, or h. If we run out of those, typically what mathematicians do is, I know this might not seem exciting, but they use capital letters for them. It makes it a little bit easier. Now, remember, this is the name of the function. If you really wanted to, you could name them like that. Call this one Harvey instead of F. That's perfectly fine. Harvey of x equals, say, 7x plus 22. However, if you're using this function name a lot of times, you might get tired of writing down Harvey all the time. That's why F, G, H, capitals F, G, and H are the ones that are most likely used. And last of all, remember, this is the independent variable. This whole thing is the dependent variable, y. Again, this is not f times x. And this represents, take 2 for x, put in the function for every x, change every x to a 2, and then evaluate it either mentally or with your calculator to find out what the y value is. So remember, this gives you an ordered pair. 2 is your x value, and whatever you get from f of 2 is your y value. Next, here we've got two functions, and we want to find out what f of 2 is. Well, here's our f function, so we're going to take f of 2, and we're going to rewrite this, but every place we see an x, we'll put a 2. So minus, there's our 2, and this represents minus x squared plus 5 times x. This time x is 2 and minus 3. Just evaluate that. 2's in, get your second coordinate. So this represents the ordered pair. 2 because that's what you use for x, and that's what you got for y using function f. How about f of q? Okay, this is a bit of a curveball, but if you go back here and look at what we did, we took this number and put in the function everywhere we saw an x. So we're going to just do that. So our f of x is minus x squared plus 5x minus 3. Simple, just copy it. Now this says every x is going to be replaced by a q, okay? So f of q is what? We'll get minus, and where the x is, you put a q. Where every x is, you put a q. That's all there is to it. You already had what you needed to actually figure that out. There are the q's. Now this says, how about this? Well, this sort of pushes you a little bit further than the last one. So we're talking about function g. Here's function g. G is 2x plus 3. Now this means you're going to take a plus 1 and put in any x you see up here. So there's your function. Put in a plus 1 where the x's were. And simplify if possible. And there's your answer. It's really that simple. Next, f of 3. What's this mean? This means the f at 3. The f value at 3. So put the 3 in where the x is in function f and evaluate. And remember that represents the ordered pair. Remember this is the x, 3. What y value do we get for that? A 2. There, this represents the ordered pair 3, 2. Just in a different way, talking about function f. How about f of 3 here? Now, you might look at this and say, oh my gosh, I really don't know how to do this. But actually, remember, these functions are special ordered pairs. And this represents the x value. What ordered pair here has an x of 3 right here? So what's f of 3? For a 3, you get a 1. And there you go. F of 3, again. Where's the x value? There. Where does the arrow take us? To a 5. So f of 3 is 5. It's just a different way of doing the same thing. Next, find f of 3 here. All we need to do is go over to the x value of 3, which is here, and then go either up or down to where the actual graph is. And there's your point. At 3, 4. 3 from here, 4 from the graph. Now, if you want to take an equation that has x and y's, find an expression for f of x. 2 steps. First of all, solve the equation for y, and then just take out the y and replace it with f of x. How does that work? Well, very simple. First of all, function notation for this. Take out the y and just put in f of x. It represents the same thing. There's your function. Now it says find f of negative 2. So f of negative 2 means you take the negative 2, put it in everywhere you see an x over here. So negative 2 in for this x, and that's the only x, so we're in good shape. And for negative 2, what do we get? And what do we get for f of p? Can you do this by yourself? There's f of negative 2. So f of negative 2 is 5. Remember, that represents the order pair negative 2, 5. How about f of p? We'll just put p in f where the x's are. And there you go. That's f at p. Next up, rewrite each one using function notation. Then find f of negative 2 and f of p. All right, so we'll take the x minus 4y equals 5. I want to get y equals. So the first thing I'm going to do is I'm going to subtract x from both sides. There we go. And I need y, so I'll divide by negative 4. It'll give me y here. And negative x plus 5 over negative 4 would be one way of writing it. Or if you want to, you can write it as y equals 1/4 x plus, minus 5/4. And last of all, we want function notation. Put an f of x where the y was. Easy. Now f of negative 2. F of negative 2. I'll use my function notation down here. I can get that value by taking 1/4 of what? The negative 2. And then at the end, I'm going to subtract 5/4. I'll let you do that for a change, okay? We'll see it in a second here. F of p. Now go back down here. Every x becomes a p. 1/4 p minus 5/4. There's f of p real fast. So f of negative 2, the negative 2 in there, you get negative 7/4. Is that what you got? I hope so. F of p, real easy. Just replace the x's with p's. Moving on, increasing, decreasing, and constant functions. Excuse me. Okay, first of all, let's get something out of the way right away. This just means that if you're looking at the Cartesian coordinate system, the rectangular coordinate system, then this number comes on the left, this one comes on the right. So actually you're moving from x1 to x2 on your graph. So all three of these say the same thing. x1 comes before x2. Now, increasing means that the y values get bigger. So this going from left to right means the x's are getting bigger. And increasing means the y value gets larger. If it's decreasing, then we're going from x1 to x2, and that means the y gets smaller. And third, it's constant if no matter what x you go from or to, the y value is always the same. So you go from x1 over to some other x sub 2, the y doesn't change. In other words, constant. So let's take a look at this one. This is a good example that you can use and see where the function is increasing, decreasing, or constant. So let's start from the left and move to the right. If I start right here, what's happening as I travel along this curve? Well, the y values are getting smaller. So, and where does this start? It starts at negative infinity. So negative infinity to where? Well, this stops at -2. What's happening? It's decreasing because the curve goes downward. Now what happens? Well, it starts going upward. So starting at -2 and going up to, well, it keeps going up until it gets there. Increasing there. And what happens after that? Going from 1 onward, notice this has an arrow so it doesn't stop. 1 to infinity, it stays constant. In other words, the y value is always at 8. And that's a summary of what we just said. Now here's an example you can try for yourself. I'm not going to go through it because it's going to show you anyway. Now, what's the maximum height of a kite? Well, this is the height right here. How high does it get? Well, it gets to about what? About 175. And that's in feet. Make sure we put the units in there so we know it's not meters. Second, it asks, what's the maximum height reached? When is the maximum height reached? When means how long did that kite have to go until it got to 175 feet? About 5 minutes. And that corresponds to 5 minutes, 175 feet as our ordered pair. Next, after it reaches the maximum height, it starts falling. What's the minimum height on the graph between 5 and 15? So we have to go, we're interested in 5 to 15. We don't care about beyond or previous to that. Where's the minimum? The minimum is right there. So it's about 10 minutes in, and it's about 125 feet up at its minimum from 5 minutes to 15 minutes. Now there are lower parts like over here and over here, but we're only interested in 5 to 15 minutes. When is it increasing? When is it decreasing? From 0 to 5, it's increasing. Oops. 0 to 5, it's increasing. Decreasing from 5 to about 10. And it's also decreasing over here. It's decreasing from about 20 to 25 when it hits the ground. So describe the height changes. Well, see if you can put some words to that. You can pause and read through that. We've actually finished this, folks. And that's talking about functions. How to describe the functions, how to use functional notation. So that's it, folks. See you next time.